Hello there. I'm going to just talk about the electromagnetic spectrum today. But before I do, I'm just going to talk about some other things quickly. So from yesterday, what I was talking about yesterday, I was saying about the TV channels utilize frequencies in the range of 54 to 88 MHz, and 174 to 222 megahertz MHz. That's right. So right, yeah, that's right. The entire FM radio band lies between channels 88 megahertz and 174 megahertz. These TV channels are called VHF, very high frequency. That's the abbreviation, VHF. And then you have other channels called UHF, ultra high frequency, utilized an even higher frequency range of 470 to 1000 megahertz MHz. So I thought I'd just mention that to you. Let's just see. What I wanted to say also, that the very low frequency VLF is 3 to 30 kilohertz, and if you write it down in hertz, if you convert it into hertz, it's 3 with three zeros after the 3, and then it goes to 30,000 hertz, so 3,000 to 30,000 hertz. I just wanted to say that to you. So if we just look at discuss bands at the moment, if I just talk about bands, you've got very high frequency. You've got ultra high frequency, you've got super high frequency, you've got extremely high frequency, and you've got tremendously high frequency. So I just thought I'd just tell you that. And what else? Oh yes, I wanted to say that yesterday when I was talking about the upper mesosphere, I was talking about that. You have the mesopause, which is sort of I find when I research things, I find that sometimes you get conflicting views sometimes, or conflicting answers sometimes. But I think the mesopause is 53 to 62 miles, and the mesopause is actually between the mesosphere and the thermosphere. So I just thought I'd mention that to you. And the exosphere, which is the layer above the thermosphere, I think when you get to the end of the exosphere, because it starts about 300 miles above sea level, the exosphere, and when you get to the end of the exosphere, I think you're halfway to the moon. Actually, you're halfway, you're sort of between you're halfway between planet Earth and the moon. So I just thought I'd mention that to you. And obviously, the advent of communication satellites in the 1960s that sort of took over from the skyways. The advent of communication satellites in the 1960s. So that's right. Many long-range communication needs that previously used skywaves now use satellites. So I just thought I'd say that to you. So I'm going to talk about I'm going to move on and talk about the electromagnetic spectrum today, if that's all right, if you don't mind. Right. I'll just talk about that. Thank you for your patience again. Right. So the electromagnetic spectrum, gamma rays have the shortest wavelengths, and hence the highest frequencies. And they are highly penetrating as well. I think they're the most penetrating form of the electromagnetic spectrum. So I just thought I'd say that to you. Right, X-rays. Now they're the ones. That's right. They're the second highest frequency on the second highest energy, the second highest frequency, and on the electromagnetic spectrum chart. So X-rays are electromagnetic waves with wavelengths in the range of 0.01 to 10 nanometers. And the frequencies are in the range of 30 PETA hertz, which I've written down. I'm going to show you this. Corresponding to frequencies in the range 30 petahertz to 30 exahertz. And energies in the range 100 eV to 100 keV. So it's a small e. These units, it's actually a small e and a big V. So I thought I'd mention that. They are shorter in wavelength than ultraviolet rays and longer than gamma rays. That's right. So that's right. So obviously the on the electromagnetic spectrum chart, the shortest wavelengths are the gamma rays, the gamma rays, and the second shortest wavelengths are the X-rays. So that's right. They are shorter in wavelength than the UV rays and longer than the gamma rays. So that's right. I just thought I'd mention that to you. And I also want to talk about the visible part of the electromagnetic spectrum. Right, the visible portion of the electromagnetic spectrum is located between 380 nms, 380 nanometers, to 750 nanometers. That's right. So red actually is 670 to 770 nanometers. So it's abbreviated to nm. So it's 670 to 770 nms. Orange is 592 to 620 nms, which is nanometers. Yellow is 578 to 590 to 592 nanometers. Green is 500 to 578 nanometers. Blue is 464 to 500 nanometers, and indigo is 444 to 464 nanometers. And red has the longest wavelengths and the shortest. Sorry, does it have? Yeah, it has the longest. I think red has the longest wavelengths with the colours, so that would make it have the shortest frequencies. And violet has the highest frequency in the colour region, and the shortest wavelength. Right, that's right. So yeah, that's right. So radio. So that's right. Red light has the lowest frequencies and the longest wavelength, while violet has the highest frequencies and the shortest wavelength. So I just thought I'd mention that to you. And obviously, red is 620 to 750 nanometers, and in the other units, it's 400 to 484 THz. So I just thought I'd mention that to you. Right. So again, a typical human eye will respond to wavelengths from about 380 to 740 nanometers. In terms of frequency, this corresponds to a band in the vicinity of 430 to 770 THz. So I just thought I'd mention that to you. Now, gamma rays are very high frequency electromagnetic waves. That's right, usually emitted from radioactive decay with frequencies greater than 10 to 19 Hertz. Gamma rays are the highest energy electromagnetic radiation and have energies greater than 100 keV, so it's a small e and a big V again, 100 keV. Frequencies greater than 10 to the 19 Hertz, so that's right. And wavelengths less than 10 picometers. Right. And I just want to show you this now. Just a minute, I'll just show you this. Sorry. Thank you for waiting here. Right, I've got here X-rays here. Electromagnetic waves, X-rays. And wavelengths from 0.01 to 10 nanometers. That's right. So they're wavelengths. The X-rays, electromagnetic waves, with wavelengths 0.01 to 10 nanometers. A frequency for the X-rays is 3 times 10 to the 16 hertz to 3 times 10 to the 19 hertz. Just thought I'd show that to you. And frequencies, that's right, so that's frequency 30 petahertz to 30 exahertz. And energies 100 eV to 100 keV. So I just thought I'd just explain that to you today. And then I've got here the gamma rays. I haven't actually written it down, but gamma rays, energies greater than 100 keV frequency, greater than 10 to the 19 hertz, and wavelengths less than 10 picometers. So I just thought I'd mention that to you. And on the other side, I've just sort of done a bit of a flimsy thing here, but I've done the so yeah, I've got gamma. The highest frequency and the highest energy is gamma. Then second it's X-rays, third it's ultraviolet, then it's visible, then it's infrared, then it's microwaves, then it's radio waves, in that order. And then obviously the longest wavelengths is radio, then it's microwaves, then it's infrared, then it's visible, then it's ultraviolet. And then, so I just thought I'd show that to you. Thank you for looking at that. Okay, so I'll just go back to what I'm going to talk about now. Yeah, so, right, thank you for that. Yeah, so which type of radiation has the shortest wavelengths? Well, that's gamma rays. And which radiation has the highest frequency? And that's gamma rays as well. So I just thought I'd just, so yeah, I thought I'd mention that to you. Right, we see the longest light waves as the colour red. Waves that appear red are about 700 nanometers, right? That's right. So the shortest light waves are 400 nanometers in length, are seen by the human eyes as the colour violet. So I just thought I'd mention that to you. Right. The highest energies of the ultraviolet spectrum from wavelengths, that's right, the highest energies of the ultraviolet spectrum from wavelengths about 10 nanometers to 120 are ionizing. So that I think that's the extreme for ultraviolet, or ionizing. That's right. So that the higher energies of the ultraviolet spectrum from wavelengths about 10 nanometers to 120, and I think it's extreme ultraviolet or ionizing. So the higher part of, we know that the ionizing part of the electromagnetic spectrum are X-rays, gamma rays, X-rays, and the higher ultraviolet part of the electromagnetic spectrum. But the lower part is considered non-ionizing, and that also applies to this applies to infrared, visible light, microwaves, and radio waves. And again, and of course, the lower part of the ultraviolet light is considered non-ionizing, but the ionizing ones, highly ionizing, of the higher part of the ultraviolet light, and X-rays and gamma rays. So I just thought I'd say that to you. Right, X-rays have shorter wavelengths than UV waves, and generally longer wavelengths than gamma rays. Because X-rays have very high energy, they are known as ionizing radiation and can harm living tissue. So yes, X-rays are broken up into X-rays are broken up into broad two categories: hard X-rays with energies above 5 to 10 keV, and below 0.2 to 0.1 nanometers in the wavelength, and soft X-rays with energies 100 small e, big V, and then to 5 keV. So that's a small e and a big V, and 10 to and the number 10 to 0.1 nanometers in wavelength. Hard X-rays are more useful for radiography because they pass through tissue. So I just thought I'd say that to you. Right, so yeah, the shortest waves, the X-rays and gamma rays have the shortest wavelengths and carry the most energy. They are also the most penetrative of the electromagnetic waves, a property which is useful in medical imaging. I just thought I'd mention that to you. Yeah, so right, yeah. Right, the ozone layer is a region of the stratosphere between 50 and 30 kilometers in altitude, containing a relatively high concentration of ozone. It absorbs most of the solar ultraviolet radiation. So yeah, an ionizing radiation is high energy radiation that is capable of causing ionization in substances through which it passes. Also includes high energy particles. And non-ionizing radiation that does not cause atmospheric ionization, so it's electrically neutral radiation. Ultraviolet light is UV, is electromagnetic radiation with a wavelength shorter than that of visible light, but longer than X-rays. That is in the range of 10 nanometers to 400 nanometers, corresponding to photon energies from 3 little e, 3, so the number 3, small e, big V, to 124, small e, big V. I just thought I'd mention that. So yes, I just thought I'd say that to you. Waves shorter than light, such as UV, X-rays and gamma rays, are very energetic and can penetrate some solid materials that block light. That makes exposure to them dangerous. So I just thought I'd say that to you. Yeah, so as we know, X-rays have slightly longer wavelengths. Sorry, that's right. Yeah, so I just thought. Yeah, so yeah, sorry. X-rays, they are less penetrating than gamma radiation, but are still harmful to living tissue. That's right. So that they are less. So X-rays are less penetrating than gamma radiation, but are still harmful to living tissues. So I just thought I'd mention that. Right. Right, so like gamma rays, X-rays are absorbed in different amounts by different materials, and so they can be used for industrial radiography. They can form good images of the human body because bone and soft tissue absorb the rays by different amounts. Right. I just thought I'd mention that. Right. That's right. Let's see now. Yeah, so X-rays with photon energies above 5 to 10 keV are called hard X-rays, while those with lower energy are called soft X-rays. Due to their penetrating ability, hard X-rays are widely used to image the inside of objects. So that's right, in medical radiography. So I just thought I'd mention that. Right, in medical diagnostic applications, the low energy soft X-rays are unwanted, since they are totally absorbed by the body. So I just thought I'd say that to you. So yeah. Right, yeah. UV. Sorry about this. Right. Not all electromagnetic not all electromagnetic radiation is ionizing. Only the high frequency portion of the electromagnetic spectrum, which includes X-rays and gamma rays, and the higher ultraviolet part of the electromagnetic spectrum, are ionizing. So I just thought I'd say that again to you. Right. So as we know, with visible light, violet has the highest frequency. It's 380 to 450 nanometers. Then blue is 450 to 495 nanometers. Green is 495 to 570 nanometers. Yellow is 570 to 590 nanometers. Orange is 590 to 620 nanometers. And red is 620 to 750 nms, if I abbreviate the nanometers to nms. Right. Gamma rays are now usually distinguished by their origins. X-rays are emitted by electrons outside the nucleus, while gamma rays are emitted by the nucleus. That's right. So X-rays are emitted by electrons outside the nucleus, while gamma rays are emitted by the nucleus. So I just thought I'd put you in the picture a bit there, because I know I'm still going to talk about the electromagnetic spectrum. Right, so yeah, if I just very quickly say something else now. The ultraviolet frequency is in THZ for the, sorry, I take that back. For the visible light, violet is, the frequency is THZ, so it's 680. Violet is 680 to 790 in the THZs. Blue is 620 to 680 in THZs. Green, I think, is 530 to 600 in THZs. Yellow is 510 to 530 in THZs. Orange is 480 to 510 in THZs, and red is 405 to 480 in THZs. So I think that might be some rough estimates there. So just, if you're not sure, because you could always look it up. Let me have a look now to see. Sorry. Just a minute. Right. Just want to show you something else now today. Sorry about that. Thank you for your patience. Right, if I just put that there for you, just want to show you that today. And I also want to show you that as well. If that's all right. Thank you for just made some notes on some stuff I thought it might be interesting for you. Thank you for being patient. I just want to Right. Thank you for being patient today. Anyway, just Right. If I put this now, I'm just going to write something down here. Sorry. Thank you for... Oh, lovely. Sorry, thank you for that. Thank you for waiting. Yeah, so if I just put... Right, I've got this here. And I think they use that for smints, don't they? That's the main ingredient of smints, isn't it? The mints. So I just thought I'd put that down for you. And then if I just write this one down for you. Right, paracetamol. I haven't spelt the word properly. I'm sorry about that. But anyway, I think I've got the formula right. It's C8H9 and NO2. I think that's so. It's 8 atoms of carbon, 9 of hydrogen, 1 of nitrogen, and 2 of oxygen. So I just thought I'd show that to you. Now, just want to just do one more thing, and then I'm just going to wrap things up now. But just want to right. I just want to show you. I just want to talk about something now. Yeah. So the just see here. Yeah. The DICHLOROBENZYL alcohol is an antiseptic, I think, and the AMYLMETACRESOL is also amyl. It's hard to pronounce, and it's also an antiseptic. Is it? I think found. That's right. So I just thought I'd mention that to you, and also for antibacterial sort of stuff. That's the COCAMIDOPRPYL betaine, BETAINE, and its formula is C19H38N2O3, and I think that's used in antibacterial for washing, for so it's in soap, so I think it's a component. It's actually in the it's one of it makes up its composition of soap, doesn't it, for antibacterial stuff. So I just thought I'd mention that to you. So yeah, and that's right. And the other one, phenoxyethanol. So its chemical formula is C8H10O2, and that's an antiseptic. And then I think some of these ones are actually in fairy liquid. So if you look at a bottle of fairy liquid, you get methyl. Anyway, so it's C4H. Sorry, C4H4. ClNOS, I think, and then there's another one actually, methy, which I've already shown you on that bit of paper. It's C4H5NOS. So yeah, I thought I'd just show you that. Anyway, I think I've covered quite a bit today. So thank you for your patience. Anyway, thank you very much. Thank you.